welcome back. We have been continuing to talking about designing principle of chemical reactors, and so today's topic is also going to be continuation of the same. And if you recall, we discussed one problem of CSTR conversion in the previous class. We will continue and we will discuss some more problems. So, let us then define another problem here. We are going to consider this particular reaction, liquid phase reaction, and this is following an elementary rate law, which means minus R A equals to K into C A into C B. So, both are first order. Now, to do this reaction, what we have is two reactors that are available. Either you can do this reaction in a 800 decimeter cube plugged flow reactor, which is operated at temperature of 300 Kelvin. So, this is the volume of the plugged flow reactor, or you can do this reaction in a 200 decimeter cube CSTR, which is operated at a temperature of 350 Kelvin. Now, for both these flow reactors, either you do the reaction in this or you do the reaction in this. Basically, the inlet stream is consisting of two separate feeds of A and B. They come together and they form one single inlet stream, and in this inlet stream you have basically equal molar A and B, and the total volumetric flow rate is 10 decimeter cube per minute. And also what is given is you know that there are two separate streams that are coming for A and B. They are coming together and forming one inlet stream, and that is entering your reactor. So, these two separate streams, the concentration of A in one stream, which is before mixing, concentration of A is basically 2 moles per decimeter cube, and concentration of B before mixing is also 2 moles per decimeter cube, and the volumetric flow rate of A is before mixing again is 5 decimeter cube per minute, the same as volumetric flow rate of B. And also, since the reactors are operated at different temperatures, you need to know the K value at these two different temperatures. So, what is given is the K value at 300 Kelvin is 0.07 decimeter cube per mole per minute, and the activation energy is 85,000 joule per mole Kelvin. So, all these things are given. Now, the question is which of the two reactors is going to give you a higher conversion. So, if you want to pictorially depict this thing, at least for CSTR we will depict, you can do this for PFR after. It is something like this. So, you have the CSTR, this is the stirrer, and this is the reaction mixture where it is operating. So, one stream is coming for A separately, another stream is coming for B separately, and they are coming together. They are coming together and entering into the reactor, okay. And whatever is coming out has a separate molar flow rate out for A say and for B also, and X is the conversion. X is what we are going to find out. And so, this is CSTR we are talking about. So, CSTR is operated at 350 Kelvin and the volume is 200 decimeter cube for the CSTR. And also, so this is a separate stream of A is coming and separate stream of B is coming, and then they are coming together. And in this you have equal molar A and B, and here also if you are looking at Ca0, I am just putting small b. So, Ca0 before mixing is 2 moles per decimeter cube. So, from here and from here Cb0 before mixing is 2 moles per decimeter cube, and this is, so the molar flow rate in is Fa0 here, it is Fb0. So, when they mix up, obviously the concentration for A becomes half and concentration of B becomes half, and the total volumetric flow rate is basically 10 decimeter cube per minute. So, volumetric flow rate of A here is 5 decimeter cube per minute, and here it is they are coming at 5 decimeter cube per minute. So, when they come together it is 10 decimeter cube per minute. So, at least this is the definition of problem for CSTR. The same thing you could do for PFR also. This is just to pictorially depict the meanings of these things, because you might be confused, what do you mean by before mixing, what do we mean by before mixing and after mixing. So, that is the situation. So, this is before mixing and then they mix and then they enter. Now, let us try to solve this problem. Okay. So, what is the mole balance of CSTR? It is Fa0 into Xa divided by minus Ra. And what is the mole balance? Actually, this is the design equation that we get from the mole balance. So, what is the design equation of Vpfr of PFR? So, you will get the Vpfr from there. So, that is Fa0 into 0 to Xa dxa divided by minus Ra. Rate law we already know, this is the rate law. So, stoichiometry, now step by step let us proceed. We go to the stoichiometry. Concentration of A is equals to Fa into 1 minus x divided by small v, and that is equal to, so this is Fa0 into 1 minus x by small v is equals to Ca0 into 1 minus x. This is appearing everywhere. So, I am not going to explain again how this appears. Even before, when we constructed the stoichiometric table, we had discussed about this. So, this is the expression. So, if you put this value, this here in VCSTR, this expression in VCSTR, it will be equal to Fa0 into Xa divided by, remember, minus Ra is equals to K into Ca into Cb, okay. And Ca and Cb are the same, Ca0 and Cb0 are the same, we have already talked about that. So, this will be Fa0 into Xa divided by K Ca0 square into 1 minus x square, because Ca is this, Cb is also this, equal molar flow. Okay. What about Vpfr? It is Fa0 into integral 0 to Xa dxa, express write the expression of Ra minus Ra, it will be K, the same expression as this, into 1 minus x whole square. I am just putting x, it will be Xa actually, okay, x subscript a. Now, this K Ca0 square is constant, they come out, so on and so forth. What is the value of small k at 350? Now, remember, the value of small k at 300 is given, rate constant at 300 it is given, and the energy of activation is also given. So, if you know the temperature at which you have to find out the rate constant, so in this case say 350, then what you do? Your expression of k is nothing but A into e to the power minus E by RT. So, this is the value of k at that particular temperature. Now, this value is given at 300, A we do not know, we do not need to know also in this case, T we know, for 300 degrees it will be 300, and E we know, activation energy, that does not change with temperature. So, what we can do is that we can take a ratio of K 350 to K 300, then this A will cancel out and we will get what you have as E to the power E by R, e to the power E by R into 1 by 300 minus 1 by 350, and this value is already known, this value is 0.07 decimeter cube per mole per minute. So, if you solve for this, just take the ratio between the two. So, this A cancels out, you do not need to know the A, you know the value of E. So, from here your K 350, that means the rate constant at 350 Kelvin is 8.447 decimeter cube per mole per minute. Okay. Now, let us solve this expression, because we want to know VCSTR is already known, we want to find the value of x, that is what we want to find. Now, remember that this reaction is done at 350 Kelvin, 350 degree Kelvin at 350 degree Kelvin in the CSTR. So, the value of K that you are going to use is at 350. So, that is the value of K that you are going to use. So, if you now put those expressions here, what you will get? CSTR at 350, this 1 minus x whole square is 1 minus 2x plus x square, this equals to, this term is Fa0 into xa divided by k Ca0 square, this v comes here, this, okay, this into x, just putting x here, okay, this is the term. If you rearrange this, what you will get is a quadratic expression in terms of x, Fa0 divided by k Ca0 square into v plus 2 into x plus 1 equal to 0. This is a quadratic expression that you will get. So, this you can easily solve. Remember, this value is also known. What is this value? This value is nothing but Fa0 divided by k Ca0 square into v. This value is nothing but Fa0 is 10 mole per minute. Already it was defined in the problem that your inlet stream, what is the volumetric flow rate in, that is 10 decimeter cube per minute, the total volumetric flow rate in. But if you look at the picture here, your Ca0, which is the concentration before mixing, is 2 moles per decimeter cube, and what is the volume of volumetric flow rate in of A? It is 5 decimeter cube per minute. So, you have to multiply these two, and if you multiply these two, you get the value of Fa0, which is 10, the value of Fa0 is 10 moles per minute. So, that is 10 moles per minute, small k is 8.447, we already determined the value of small k at 350 Kelvin. So, 8.447 decimeter cube by mole minute. Ca0 is basically 1 moles per decimeter cube, that whole square, 1, because ultimately the entering concentration has become halved. It was 2 moles per decimeter cube here, 2 moles per decimeter cube here for A and B. So, when they came together, the Ca0 at the entrance is basically 1 moles per decimeter cube. So, the Ca0 is 1 moles per decimeter cube, and V is already known. What is the volume? It is 200 decimeter cube. So, if you solve this thing and if you put here in this expression, so remember this expression is your a quadratic ax square plus bx plus c equals to 0. If you have a quadratic equation like this, ax square plus bx plus c equals to 0, then your x will have two solutions. It will be minus b plus minus root over b square minus 4ac divided by 2a, and both solutions may be feasible or only one solution may be feasible depending on if it is physically possible or not. Here only one solution is feasible, you can work it out, and the value of x from here that you will get, because you know this value, will be equal to 0.926. So, 92.6% conversion, 92.6% conversion. So, what will be the corresponding value for PFR? For PFR, remember your expression was Fa0 divided by k Ca0 square into integral 0 to xa dxa by 1 minus x square. I mean, I am using x or xa interchangeably, you can understand that both are the same. So, if you do the integration and do a rearrangement, basically what you will get is k Ca0 square into Fa0. So, this goes here divided by Fa0 into V, which is the V PFR, that becomes equal to, if you do the integration here, it will be x divided by 1 minus x, xa divided by 1 minus xa. So, if you put all the values, you know these values of Ca, you know the value of Fa, and you know the value of k. Now, this value of k has to be the value of k at 300, because the PFR is operated at 300 Kelvin. So, if you put all these things, your x becomes, or xa becomes 0.84. So, basically if you are using a CSTR, you will get a higher yield, around 93% yield, and if you are using a PFR, you will get a lower yield. So, that is the solution of the problem. Now, let us solve a problem, a simple problem for polymerization. Let us say we are going to use a batch reactor and we are polymerizing pure styrene at 60 degree Celsius with benzoyl peroxide as the initiator, okay. And we are going to use a batch reactor and we are aiming for 10% conversion. This is our aim, and what is given is the initiator efficiency is 1, let us assume that. The value of Kp square by Kt, this is the propagation rate constant, this is termination rate constant. This value is equal to 0.95 into 10 to the power minus 3 liter per mole per second, and the concentration of the initiator is given as 4 into 10 to the power minus 3 moles per liter, and dissociation constant is given as 1.92 into 10 to the power minus 6 per second. So, the question is, what is the time required to obtain 10% conversion in a batch reactor? Now, remember that we had solved for a first order reaction previously, we had solved this expression. This was the expression that we had got if the reaction is first order. In order to get this kind of conversion, we have this expression. Now, if you replace this x, the conversion, remember conversion is nothing but initial concentration minus final concentration divided by initial concentration of the monomer. If you are looking at a polymerization, you replace that here, then let us just assume in this case it is a first order reaction for styrene. So, if you put that value here, what you will get is nothing but, now we are solving the problem solution, we will get ln m by m0 equals to minus Kt. So, we are basically getting from here by replacing xa with this value. Now, this k is basically equal to Kp into f Kd divided by Kt to the power half into I to the power half. If you recall the expressions of the rate that we had, then this is the value of k. So, if you recall what we discussed about in the during the classes on the analysis of the kinetics for the rates of polymerization, so on and so forth. So, then you can realize that this k will be something like this. So, if you take the square of that, that will be Kp square divided by Kt into f Kd into I. Okay. Now, you know all these values, you know the value of Kp square by Kt, put that value here. Kp square by Kt is this, f is 1, I is already known, Kd is also known. So, what you will get is 7.30 into 10 to the power minus 12 second square inverse. So, that means your value of k will be square root of that, which will be 2.70 into 10 to the power minus 6 per second. So, you now put this value here, then what is the expression you will get from here? If you put the value there, you will get ln m by m naught equal to 2.7 into 10 to the power minus 6 into t. There is a minus term there. Okay. So, if you do the calculation here, what you will get? You will get from here, let us say you are going for 10% conversion, then your m0 minus m divided by m0 is 0.1. So, from there you can get this expression of m by m0. So, if you use this expression here in this term, it will come out as 0.9. So, it will be basically ln of 0.9 will be equal to minus 2.7 into 10 to the power minus 6 into t, and if you solve that, t is your 8.1 hour. So, that is how you get your final expression. In this case, we assumed that the styrene polymerization is first order, okay, and a low conversion, of course. All right. So, okay, so we have done one simple problem for polymerization here. Now, what we are going to do is the following. Let us try to probably work out one more problem. Let us try to work out one more problem. Okay. Say, let us say we are trying to prepare polyethylene and you are using a tubular reactor. It could be a plugged flow reactor also, and the dimension here is 2.5 centimeter diameter and 1 meter long tube, and the reaction is done at 250 degrees Celsius and 2500 atmospheric pressure, and conversion per pass is 30%. Also, what is given is the flow rate. The flow rate is 40,000 kg per hour, and also you assume that the polymerization is first order in ethylene concentration. So, all these things are given. Then the question that is being asked is you should try to estimate the value of the rate constant for propagation. So, it is a ethylene polymerization is being done. So, product is polyethylene. Ethylene polymerization is being done in a tubular reactor of this dimension. This is diameter, this is the length at 250 degrees Celsius and 2500 atmospheric pressure at high pressure, under high pressure, and the conversion per pass is 30%, flow rate is this. So, what is the value of Kp? This is the question. So, remember that this was the plugged flow reactor that we talked about, and then if you have a small element, small volume element here, say mass m is going in and m plus dm that is going out, so molar flow rate in, molar flow rate out, so on and so forth, and this dV is the volume of this. Now, if you write down the design equation here, if you remember, it is Fa0 into integral 0 to x xa dxa divided by minus Ra. This was the design equation. Okay. So, from here what you can actually write down is the following: Fa0 dxa dV is equals to Ra. Fa0 dxa dV is equals to Ra, and from this expression your Fa0, which is the molar flow rate in, this is the molar flow rate in, right, So, this molar flow rate in is basically equal to volumetric flow rate in into the mass that is going in, the concentration, let us say concentration, in this case the concentration of the ethylene, let us say that is going in, this dxa dV equals to the rate of polymerization. Basically this is the rate of polymerization, the rate of propagation, it is the rate of polymerization. Now, if you do an integration here, so let us say you do an integration from volume 0 to V and you do the corresponding rearrangement, it will be dV by V small v into m0 equals to 0 to xa dxa divided by rp. Okay. So, this is the expression that you will get here. Okay. So, this is dV by V m0 and then this side dxa divided by rp, that will come. Now, if you remember, your value of xa is nothing but m0 minus m divided by m0, this is the value of xa. So, what is the value of dxa? The value of dxa is nothing but minus dm by m0. So, you replace that value here and then what you will get is the following: 0 to v dv by small v into m0, small v into m0 equals to now you are replacing xa by m. So, this integral will also change from initial value of m to final value of m. So, if you put those values here, that will be m0 to m minus dm divided by m0 into rp. Okay. So, finally, what you will get is this small v comes out and when you integrate from 0 to v, the dv, it becomes capital V by small v, this equal to integral m0 to m, m0 goes here. So, this is minus dm divided by rp. This is the final expression that you have. Now, your rp is nothing but Kp into m. Rp is nothing but Kp into m. So, if you are putting that expression here, what you will get? What you will get here is capital V by small v equals to minus integral m0 to m into dm by m, because remember that the reaction is first order in ethylene, that is what we talked about. This Kp value we are trying to find out. Okay. So, if we put that value here, so Rp is replaced by Kp into m. So, that will be Kp into m. So, if you put the Kp out of the equation, that will be Kp into capital V by small v equals to minus integral m0 to m dm by m. This is your residence time, capital V by small v. So, it will be Kp into tau equals to minus integral m0 to m dm by m, and if you do the integration, ultimately what you will get is m equals to m0 into e to the power minus Kp tau, and also what you will get is the value of Kp, which will be nothing but minus 1 by tau to ln m by m0. You are trying to find out the value of Kp here. Now, m by m0 you already know, it is 0.7, because you are looking for 30% conversion. So, that is m by m0. So, if you put that value here, then it will be minus 1 by tau ln 0.7. Now, what you have to find out, the problem has been reduced to finding out the value of tau, the residence time. Then you can find out the value of the Kp or the propagation constant or the rate of polymerization corresponding the rate constant. So, tau is equals to capital V by small v. Capital V is the reactor volume. So, the reactor volume is nothing but a cylindrical reactor, pi r square into L. R is the radius, L is the length. So, if you put those values, and because r is in centimeter, so you have to go to the meter, into 1 meter is the length, So, ultimately what you will get is 4.9 10 to the power minus 4 meter cube, that is the capital V. Now, what is the small v? Volumetric flow rate in, what is the small v? Let us say ethylene is in, if it is in gaseous state, you can use this ideal gas equation P v equals to nRT. So, your V equals to nRT divided by P, P being the pressure. Now, N is the number of moles, right, and the question actually mentioned, the problem mentioned that the flow rate is 40,000 kg per hour. So, correspondingly if you change that to number of moles, what you will get? N equals to 40,000 divided by the molecular weight. So, that will be this moles per hour, and this I have calculated as 1.43. This calculation is already done. I am trying to explain the principle to you, moles per hour. Okay. Now, this R is known, universal gas constant, and your T is also known, 250 degree Celsius. So, you just convert that to Kelvin and you put all the values here, then your small v is nothing but 1.43 into 10 to the power 3 moles per hour, and the value of R is basically 0.08206 meter cube atmosphere mole Kelvin into your temperature is 523 Kelvin, you can convert to Kelvin, divided by P, which is 2500 atmosphere. If you can work this out, it will come out as something like this, 24.55 meter cube per hour. So, this is what it boils down to. So, what will be the residence time then, because residence time is what you have to find out, so that you can put in this expression. So, if you write down the residence time, capital V by small v, capital V is already known, this is the capital V, 4.9 into 10 to the power minus 4 meter cube divided by small v is 24.55 meter cube per hour. So, if you work this out, it is 2 into 10 to the power minus 5 hour. Then the expression of k is nothing but minus 1 by tau into ln 0.7. If you put that value there, the value of k will come out as 4.95 per second. Okay. So, that is how we solve this thing. So, what we will do is we will stop here today, and tomorrow we are going to go to a different concept. We are going to because we have talked about mole balance until now, we will now go into a topic of what we call as energy balance, and then we will talk about different kinds of steady state conditions for reactors, especially for CSTR. So, until then, thank you and goodbye.